this video, I'd like to talk a bit about the different types of maximum and minimum we're going to be interested in. And there are going to be two types. So there is going to be global maxima and global minima. So these are where the value of the function is larger or smaller than all the possible values. And then there are also local max and local min, which are where the value of the function is bigger than just the nearby values or smaller than just the nearby values. Okay, so let's get started. So let's start off with absolute max and absolute min. So let's suppose we have a number c in the domain of f. Then we say that f of c, the value at c, is, okay, the absolute max value of f on our domain D if the value of the function at c is bigger than the value of the function everywhere else, right? So f of c is bigger than all the other values f of x, wherever we consider it, whether x is far away or nearby or wherever, okay? And similarly, f of c is the absolute min of f on D if f of c, so the value at c, is less than all the other possible values of x, of f. So if we think about it on a picture, the absolute max value will be where the graph is the highest. The absolute min value will be where the graph is the lowest. Okay, and then there are a couple of other terms that are pretty much interchangeable with absolute. So people also call these global. So sometimes I will say absolute, sometimes I will say global, but it's the same thing. And if we think of max and min together, they're sometimes called extreme values. So an extreme value can be either a max or a min. Okay, so the key point here is that absolute max or absolute min means that the value of the function is bigger than all the other possible values or smaller than all the other possible values. And then let's contrast this with local, which is where we only compare with nearby values. So as we suppose that f is defined near to c, meaning that it's defined on both sides close enough. So it doesn't matter what happens far away, but we want to be able to compare to things on both sides. So in particular here, we don't care about endpoints. So if our function is defined on a closed interval and it has, say, endpoints, say 0 to 1, then we don't allow local max and local min endpoints. So this is only for interior points. Okay, then we say that f of c is a local max value if f of c is bigger than f of x. So the value of f at c is bigger than the values of f where x is near to c. So we only compare to nearby points, and the value at c should be bigger than the values at nearby points. Okay, and similarly for the min, right? So the value of f at c should be less than the nearby values. So what does this look like on a picture? As we'll see in a second, it means, f of c is a high point, but it's only a local high point. So it's kind of like a roller coaster ride. You're at the top, but okay, maybe somewhere else you will go even higher. But for the moment you're at the top, or for the moment you're at the bottom. Okay, and these are also called, just to make things as confusing as possible, local max and min are also called relative max and min. And as I said, they cannot occur at endpoints. Okay, so let's see it here kind of summarized in a picture. So if we start off on the left, at a we have an absolute max, right? So it's bigger than all the other possible values of the function, but it's not a local, excuse me, it's not a local maximum because we're at an endpoint, right? So we cannot hope to compare it to anything on the left because the function is not defined there. So we don't admit it as a local max. This is just an absolute max. Okay, and if we, if we move along to say the local max, here there's a local maximum because the value of the function is bigger than all the nearby values, but it's not an absolute max because there is a bigger value somewhere over here. Okay, and then similarly, the same thing for the local min and the absolute min, right? So here is the absolute min. It's the smallest possible value of the function. It's lower than all the other values, but it's not a local min because we can't compare it to things on the left and right. So we do not allow a local to be endpoints. And then here is a local min, right? It's smaller than the nearby values, but it's not smaller than a value sitting over here. So here is the difference between the absolute and local. And it is possible for points to be both local and absolute. And we'll see an example in a second. But at least in this picture, the absolute and the local are different. Okay, so yeah, here is an example where that's the case. So if we look at f of x equals cosine x, say on the real line, then okay, if we look for the maximum values, okay, clearly the largest possible value is 1. And where does that occur? Okay, it occurs at 0, 2 pi, 4 pi, and so on. So if you think of this function just be defined on the whole real line, it's, say we just focus on 2 pi for the moment. The value of the function at 2 pi is 1, and that's bigger than or equal to all the other possible values. So that's an absolute max. But we can also compare it to values on both sides, and it's bigger than all the values on both sides as well. Or when I say here bigger, I mean bigger or equal to. If I mean strictly, then I will insist on saying strictly. Okay, so this is both a local and a global maximum. And we can say the same thing about 4 pi or 6 pi or any even multiple of pi. So cosine x has local and global max values of 1 at x equals 2n pi, so even multiples of pi. And then we can say the same thing at -1. For instance, if we consider the value at pi, okay, the value at pi of cosine x is -1. That's smaller or equal to than every other value of the function. So that's an absolute minimum. But also the function is defined on both sides of pi, so we can compare it to nearby things, and it's smaller than all the nearby things, so it's also a local minimum. Okay, so points can be, they can be nothing, or they can be just a local, or just a global, or they can be both. We can have anything, it just depends. So remember, absolute means it's bigger than all the other values or smaller than all the other values. Local means it's bigger or smaller than the nearby ones. But with local, we have to insist that it's not an endpoint. Okay, so moving on, here is something where it has nothing. So if we just think of e to the x, it doesn't have a local or a global maximum or a minimum. Right, so if we just pick a random point anywhere, well, on one side the function is bigger, and on the other side, the function is smaller. So there's definitely not going to be a local or a global maximum or a minimum at that point, because if I look close by, I don't see a maximum, and if I look far away, I don't see a maximum either. And okay, what's happening? You might be tempted to say, it's infinity, but we never actually get to infinity in this case. The value has to be one where the function takes that at a particular x value, right? It has to be at x equals 2 or x equals 5 or x equals something. So we don't count limits in this case. Okay, so and similarly on the left, we might be tempted to say that the absolute minimum is 0, but it never actually attains the value 0, right? So the absolute max and the absolute min and the local max and local min have to be attained. So it never takes the value 0, so there is no local or global min. Okay, so this just has nothing. Okay, so let's go on to talking about existence. So just to wrap things up, suppose we have a continuous function on a closed bounded interval AB. So notice here we're including both the endpoints. Okay, then there is an absolute max and there is an absolute min somewhere in the interval. Okay, so if we go back to e to the x, what was the problem? Okay, well, for e to the x, this was on an unbounded interval, so we can't expect this to be true. Okay, but if we have a continuous function on a closed bounded interval, then there are absolute max and there are absolute min. And let me just emphasize that here we do need all the assumptions. So if we drop, so there is continuous, and then there is closed, and then there is bounded for the interval. So if we drop any one of those, it's no longer true. So this is a useful exercise just in understanding max and min. For instance, if we drop that the interval is bounded, well, we had that example with e to the x, right? It was continuous on the whole real line. So that was one example. An easier example maybe is just f of x equals x, right? It doesn't have an absolute max or an absolute min. It goes off to infinity, it goes off to minus infinity, but it's still continuous on a nice interval. Okay, if we just drop the closed but keep it bounded, then we could take f of x equals 1 over x on 0, 1. So this is a continuous function on a bounded interval that's not closed. Okay, but as x goes to 0, 1 over x goes to infinity. So this is not going to have an absolute maximum. And then on the other hand, if we drop that the function is continuous, let's consider f of x is 1 over x on 0 to 1, including 1. Okay, and f of 0 equals 0. So we define that point separately. So it's not a continuous function anymore, but it's defined on the closed interval 0, 1. So it's defined on a closed bounded interval. But now, just as before, right, with the 1 over x piece, 1 over x goes to infinity as x is going to 0, so this is not bounded. Okay, so absolute max and min, where can they occur? So they could occur either at the endpoints, or they could occur somewhere in the middle. But in particular, if they're occurring somewhere in the middle, say I have an absolute max somewhere in the middle, then absolute max says it's bigger than all the other possible values. So in particular, it has to be bigger than all the nearby values too. So if you have an absolute max in the middle, then it's going to be also a local max. Okay, so just to summarize, absolute max and min can occur at either local max and min or at the endpoints. Okay, so over the course of the next couple of sections, we're going to figure out, how to find local max and min, how to classify them, how to find global or absolute max and min, how to classify them. So in the next time, we're just going to focus on finding absolute max and absolute min. So that's going to be our focus. Next time, we're going to do something called the closed interval method. Okay, thanks for watching, everyone. See you soon. Bye-bye.